So in the previous lecture we were talking about the common source amplifier stage with current source load. So this is what we were studying in the last lecture, and we said that we can use a MOSFET as a load. So for example, in a common source amplifier, so for example, let us draw a common source amplifier with a resistor RD as a load. Okay. So this is an NMOS over here, and this can work as a common source amplifier. Okay. So common source because input is connected at the gate and output is being taken at the drain. Okay. Now this resistor RD can be replaced by a MOSFET. Okay. So for example, a PMOS can be used as a load here. Okay. So we had discussed in the previous lecture that the PMOS can be used to source current. Okay, so that is, the PMOS can be used to source or pick the current from this node VDD, and this current can be passed to some other node, let us say X. Okay. So PMOS can be used as a current. PMOS can be used as a for sourcing the current from some node VDD to some other node, for example X. Similarly, we had commented in the previous lecture that NMOS, right? So NMOS can be used to so NMOS can be used to pick current from some node, let us say Y, and this current can be then synced to ground. Okay. So the job of this NMOS is to pick current from node Y and sync it to the ground. Okay. Or NMOS can be used as a for syncing the current to ground. Okay. So this can be used to sync current, and PMOS can be used to source the current. So in the previous lecture we had understood that these two devices can be used to either sync the current NMOS to the ground or to source the current to some node X. Okay. So that means this PMOS can be used as a load here. Okay, so it will pick the current from VDD, and this current can be sourced to this node out or X here, right? Now the gain of this circuit can be found knowing that this is a common source amplifier with drain resistance RD. So instead of drain resistance I have now a M2 load. Okay. Now looking into this port, that is towards the drain of M2, the impedance of this M2 transistor, so this would be RO2. Okay. So that means this RD is RO2. Okay. And the gain of this amplifier we had already known, it is minus GM R0 parallel to RD. Okay. So since this is transistor M1, so I write minus GM1 RO1 parallel to RD, and RD here is RO2 of M2, right? So I replace RD by RO2, so this becomes minus GM1 RO1 parallel to RO2. Okay. So which is mentioned here. So the gain of this circuit is minus GM1 RO1 parallel to RO2. Then we can also find out the output impedance. So output impedance, that is looking into the output, that is at this port, this is small signal module circuit, or directly from here Looking into the M1 from the drain side, the impedance is RO1. So the total impedance R out would be simply RO1 parallel to RO2. So we understand that this circuit can be simplified by considering M2 as load resistor, right, and then applying the same gain and the output impedance equations that we have already learned for common source amplifier to find out the gain and output impedance of this circuit. Now instead of this PMOS as a load, one can also think of using a NMOS as a load. Okay, so NMOS as a load, that is, this NMOS can be used as a load. So since this NMOS has to sink the current to the ground, okay, so that means the source of this NMOS has to be connected to ground. Okay, so one can utilize a NMOS load in the common source stage, but now the common source stage will have PMOS in the common source stage. So for example, this is my common source stage which is implemented by M2. Okay, so common source because input is at the gate and output is at the drain. Okay, so common source stage is implemented by M2. Now to this M2, load could be NMOS. So I have M2 over here, which is a PMOS, and to this PMOS my load is M1. Okay, so instead of this RD, M1, that is NMOS, is acting as a load to this common source amplifier using PMOS. Okay, now again the gain of this circuit can be found, knowing that the gain looking into the drain of M1 is RO1, okay, and the gain looking into the drain of M2 is RO2. Okay, so again one can apply the same relation, that is, for a common source amplifier the gain is this time M2, so minus GM parallel to R0 parallel to RD, sorry, minus GM multiplied by R0 parallel to RD. Okay, so GM2 RO2 and RD is RO1. So one can write this gain equation as minus GM2 multiplied by RO2 parallel to RO1. Okay, similarly the output impedance can be found by again looking into the output port from here. So the output impedance will be simply RO2 parallel to RO1. Okay. Now instead of using PMOS and NMOS as current sink or maybe the current source, okay, so one can also utilize NMOS or PMOS in a diode connection. Okay, so that is, so what is diode connection here? So for example, this is my NMOS, let us say. Okay, now if the gate and drain of NMOS are shorted, okay, so then this becomes a two terminal device, okay, where gate and drain of this NMOS is shorted. So this becomes a two terminal device, or this is actually called diode connection. Okay, now this diode connection is also valid for a PMOS, that is, in a PMOS also if you tie gate and drain, so that is called a diode connection. Okay, so now this diode connection NMOS can also be used as a load. So this is my common source stage which is implemented by M1. Okay, now to this M1, instead of resistance R, okay, so instead of resistance RD, now diode connected load is diode connected NMOS is connected. Okay, now one can find out the gain of this circuit by considering first lambda 0 and then considering lambda not equal to 0, that is first not consuming the channel length modulation and then considering the channel length modulation. So without considering channel length modulation, the gain of this circuit would be simply looking into this circuit. One can write gain is again minus GM RD parallel to R0. So this is M1 transistor, common source. So GM1 R01 parallel to RD, and since lambda is 0, so that means there is no R0. So the gain is simply minus GM times RD. So the gain is simply minus GM1 times RD. Okay, and looking into this terminal, that is source of M2, one can write the impedance as 1 by GM2 parallel to RO2. But since there is no channel length modulation, so RO2 will not be here, only 1 by GM2. So that is 1 by GM2 looking into the source of M2. So that is RD is 1 by GM2. So that means the gain of this circuit would be minus GM1 times RD, 1 by GM2. Okay, fine. Now GM1, that is GM of a transistor. So we had some time back found the GM of a transistor. I'll go back and show you. So we had found the GM of transistor by saying GM is delta ID by delta VGS, right? So GM we had found by differentiating ID with respect to VGS, okay, and then putting GM in form of ID, right? So that is GM can be written here, the same GM can be used here in the gain equation, okay, here. So GM that we had found was equal to 2 times mu n C ox W by L ID. Okay. So this GM I can use here. Okay. Now in this GM we have GM1 and GM2. So mu n and C ox and ID. These three things are same. In fact, 2 is also common in GM1 and GM2. Okay. So ID is also common because same ID. This current is flowing in M1 also. Okay. Same I. So that means these parameters will cancel out and we are left with only W by L in GM1 and W by L in GM2. So that means this gain will be equal to minus root of W by L of 1 divided by W by L of 2. Now this means that now my gain is, though it is less, but it is independent of the process parameters. This mu n and C ox, these are process parameters. So now my gain is free from process parameters. It is less dependent or independent of the process parameters. Now one can find out the gain when lambda is not equal to 0. So when lambda is not equal to 0, then one has to consider RO2 and RO1 both. Okay. So the gain equation can be modified. Okay. So we found gain as this. Okay. So from this one can modify the gain. Okay. So now the gain will be equal to, I'll write here, AV would be minus GM1 RO1 parallel to RD when lambda is not equal to 0, and RD is this time 1 by GM2 parallel to RO2. So earlier we had assumed 1 by GM2 because no channel length modulation was considered, but while considering the channel length modulation, RO2 also have to be considered. So RD will be equal to 1 by GM2 RO2. Okay. So this RD, instead of this RD, we'll write the total GM is RO1 parallel to 1 by GM2 parallel to RO2. Okay. So this is my total gain now when lambda is not 0. Similarly, the output impedance. So output impedance was earlier for a common source amplifier with source resistance with drain resistance, the output impedance is R0 parallel to RD. So R0 here is RO1 and RD is 1 by GM2 parallel to RO2. Okay. So this will become R0 1 parallel to RO2 parallel to 1 by GM1. Sorry, GM2 parallel to RO2. Yeah, correct. Okay. So R out becomes this much. So this way one can find out the gain of any other complex circuit by knowing that whether the transistors are used as a load. For example, here a diode connected load, okay, and in the previous case we had current sinks and current sources using NMOS and PMOS. Now similar to this circuit where the NMOS was used as a diode connected load, one can think of using PMOS as a diode connected load. Okay. So for example, here a PMOS is used as a diode connected load, right? So this M1 transistor is PMOS, which is used as a diode connected load to this common source stage. Okay. So this is my common source stage implemented by a PMOS transistor M2, and to this transistor the load is a diode connected PMOS. Okay. Now for this circuit also we can find out gain when lambda is not 0, okay, knowing that looking into the source the impedance is 1 by GM1 RO1, okay, parallel to RO1. So one can find out the gain as minus GM2 1 by GM1 parallel to RO1 parallel to RO2, right? Similar to how we had found it here, right? Similarly, output impedance can be found. So output impedance will be now 1 by GM1 parallel to RO1. When looking into this port it is RO2 and into this port it is this much. So total output impedance present at the output is the parallel combination of these two. Okay. Now we had discussed about the emitter degeneration in BJT based common emitter amplifier. Right. Now in a common source amplifier using MOSFET, one can also think of using a degeneration resistance. Okay. That is this RS. So this represents a degeneration resistance. We understand the advantages of using this resistor for degeneration, so we will not go into that again. Okay. So now for this amplifier circuit the gain can be found. Okay. So for example, let us say lambda is 0. Okay. So when lambda is 0 the gain can be found. Okay. Knowing that the gain of a common source amplifier with source resistance is minus GMRD by 1 plus GMRS. Okay. So one can directly write the gain as minus GMRD by 1 plus GMRS. So this is very similar to the gain of a common emitter amplifier with emitter degeneration resistance. So which was minus GMRC by 1 plus GMRE. Okay. So here in MOSFET based amplifiers we have drain resistance instead of RC and source resistance instead of RE. Okay. So the gain can be modified by inspection simply, or one can find out the gain by drawing the small signal model. Okay. So this is when lambda is 0. Now consider when lambda is not 0. Okay. So find AV when lambda is not 0. So for that purpose we draw a small signal circuit for this circuit. Okay. So in the small signal circuit we find that since lambda is not 0, so R0 is connected between drain and source. Okay. And we have RD also and we have RS also. Okay. Now one can write few relations here to find out the overall gain. Okay. So first relation would be that this V in, which is measured from here to ground, so this V in would be equal to V1 plus the potential at this point. So potential at this point is Vx, which drops across Rs. Okay. So V in is V1 plus Vx. Okay. And knowing that the current through this resistance Rd is Ix, and so that the current through R0 would be equal to Ix minus GmV1. Right, so this is GmV1. Right, so the current through R0 will be Ix minus GmV1. Okay. Now the current through Rs would be Ix, the same current, that is, which is here, so that flows into Rs. So Vx at this point can be found. Okay. So one can write Vx as Ix times Rs. Okay. Ix times Rs. Okay. Now one can also write at the output node here V out is equal to minus Ix times Rd. Okay. So I can write equation 2 here, V out is minus Ix times Rd, or I can write Ix is minus V out by Rd. Now this Ix, if I put in equation 1 here, I get equation 3. Okay. That is V in is V1 plus Ix is minus V out by Rd, I put here minus V out by Rd Rs. So I get equation 3. Okay. Now at this node V out, okay, so this V out is actually equal to the drop across this R0 plus the drop across Rs. So I can write V out as the drop across R0, which is Ix minus Gm1 multiplied by R0. Ix minus Gm1, that is current through R0 multiplied by R0 plus Vx, that is, which is Ixrs. Right. Now putting this equation number 2 and 3 in equation number 4 here. Right, so put 2 and 3 in 4, we get a relationship V out is this much. Okay. Now simply I copy this V out over here and try to find out V out by V in from here. Okay. And I found V out by V in, which is gain is equal to minus Gm Rd by R0 plus 1 plus Gm Rs plus Rs. So this much is the gain when lambda is not equal to 0. Okay. So this is the gain when lambda is 0, this gain, and this gain when lambda is not equal to 0. Now let us consider one example where a diode connected device is degenerating the common source stage. So instead of using a degeneration resistance, okay, so instead of using a degeneration resistance at the source, okay, here I am using a diode connected MOSFET. Right, so instead of using this degeneration resistance here, I am using a diode connected MOSFET M2. Okay, here. Now for this circuit, one can find out again the gain, okay, by knowing that the impedance looking into the source of M2 is 1 by Gm2 parallel to RO2. Okay. But since we are considering lambda is 0, so there is no RO2. Okay, so the impedance looking into the source is 1 by Gm2. Okay. So that is, this RS is 1 by GM2. Okay. So or if we modify the circuit, so this is 1 by GM2. Okay. So for this circuit I can find out the gain. So gain would be simply minus GM RD by 1 plus GM RD, oh sorry, 1 plus GM RS, okay. And RS is 1 by GM2 here. Okay. So one can write minus GM RD divided by 1, sorry, GM1, okay, GM1 divided by 1 plus GM1 multiplied by RS, so which is 1 by GM2. Okay. So we multiply and divide this by GM1 to obtain this relation. That is, total gain is minus RD by 1 by GM1 plus 1 by GM2. Okay. Now we have found the gain of this circuit. Now the output impedance of this circuit can also be found. Okay. So for finding out the output impedance, we need to draw the small signal model circuit. Okay. So small signal model circuit is drawn here. Okay. So in the small signal model circuit, now we are considering lambda is not equal to 0 to find out R out. Okay. So we see R naught over here and RS, which represents 1 by GM2. Okay. So that is RS, that is this RS over here, which is 1 by GM2. Okay. Now for this circuit one can find out the output impedance. Okay. So for finding out the output impedance, one has to know that this potential which is dropping across RS is Vx. Okay. And V1 is equal to minus Vx. Okay. That is, V1 is equal to minus Ix times Rs, because Vx is Ix Rs. Okay. So V1 is minus Ix Rs. Okay. Now for finding out the output impedance, we had learned that we need to short the gate to ground. Source is already shorted here, ground, via this RS, and we connect a small voltage source and measure the change in current Ix. Okay. Now the current going through R naught, so this could be found, which is Ix minus GMV1. Okay. So one can write few relations here, that is, current going through this R naught is Ix minus GMV1. Okay. And V1 we have obtained minus Ix Rs, so we put V1 from here in this equation. So we get this Ix minus GM1, that is current through R naught, is equal to this much. Then one can write a relationship by noting that this Vx, okay, so Vx is actually equal to drop across this R naught, okay, plus drop across Rs, or current through R naught multiplied by R naught plus current through Rs multiplied by Rs. Okay. So Vx is, can be written this way, current through R naught, that is this one, okay, multiplied by R naught plus Ix Rs, so this is Vx. Now from this I can find out Vx by Ix or R out, so which comes out to be equal to this much, R naught plus GM R naught Rs, right. So output impedance when lambda is not equal to 0 is this much. Now let us consider some examples of output impedance. So for example, here this is my common source stage and the load to this is the diode connected M2. Okay. So I can find out the output impedance of this by looking at the output impedance of this circuit. right? So by looking into the output impedance of this circuit, I can find out the output impedance of this circuit. Okay. So the output impedance of this circuit would be similar to the output impedance of this circuit, except RD is not present there. Okay. So the output impedance of this circuit is R0 plus GM R0 RS. So for this circuit also, the output impedance will be R0 plus GM1 R0 1 RS. Right. So this is valid for this circuit also. Okay. Now RS here represents the diode connected load M2. Impedance of this M2 looking into this port would be 1 by GM2 parallel to RO2. Okay. And considering lambda is 0, so one can write, okay, considering lambda is 0, one can write the impedance looking into this is 1 by GM2 only. So that means this RS is 1 by GM2. Okay. Or this RS here has to be replaced by 1 by GM2. Okay. So the output impedance is now RO1 1 plus GM1 multiplied by 1 by GM2. Okay. Now another example here. So now in this example, this is my common source stage, and the load, sorry, this is a common source stage, and we are using NMOS as a current sink here, not current sink source, it is for sinking the current to the ground. Okay. So that is the output. The impedance looking into this port into M2 is R02. Okay. Or this is again the same circuit, that is this circuit. So this time instead of RS we are using NMOS. Okay. So the gain can again be given by the same relation, this relation, which is rewritten over here. Okay. Now this time RS will be replaced by RO2. Okay. So the gain, sorry, the output impedance can be given by this relation then, simply replacing RS by RO2. Okay. Now let us make some modification to the previous circuits. Let us bring in this gate resistance also. Okay. So what is the effect of the gate resistance on this common source amplifier? Okay. So the effect is actually nothing. The gain and input impedance, they are not affected by the presence of this gate resistance. Okay. Because there is no conduction through gate, or Ig is 0 in a MOSFET. So this gate resistance, so this does not affect gain or IO impedance. Right. So gain, R in, R out, they all are not affected by this Rg. Okay. Because gate conducts no current for small signal frequencies. Now let us bring in this voltage divider biasing along with emitter degeneration into the common source configuration. Okay. So this is a better bias circuit where voltage divider bias and also emitter degeneration both are present. Okay. So one can find out the gain of this circuit. Okay. So for this finding out the gain, we will refer to the same circuit that we for which we had found gain using BJT. Okay. So I'll take you back to the previous lecture where we had used BJT and the rest of the circuit was same. Okay. So I'll just take you back over there. Just a second, I'll show you. Here, this one. So this circuit is a common emitter stage. Okay. And this also has voltage divider along with emitter resistance. base resistance, right? So this is similar to this circuit. Now the gain of this circuit using MOSFET can be written by looking at the gain of this circuit. Okay. So the gain of this circuit using BJT was this much, okay, where we had beta plus 1 also. I mean, in MOSFET we don't have beta, so that means the term which contains beta over here, so that will be neglected when we are writing the current gain equation for a MOSFET. Okay. So the current gain equation for MOSFET circuit would be simply RC is replaced by RD, and we don't have any RL, that is load resistance, that is this resistance is not present in our circuit, right? So no RL here, so we'll not consider RL in parallel with RD. Simply RD I'll write minus RD divided by 1 by GM of transistor number 1. So 1 by GM1 plus RE. So RE is their RS, right? So in a MOSFET based circuit it is RS instead of RE. So I write RS plus this term is 0, okay, multiplied by R1 parallel to R2. We have R1 and R2 as a voltage divider, divided by R1 parallel to R2 parallel to RS. So instead of RS we have RG, right? So we had RG here, okay, right? So this equation and this equation, so both are same, this one and this one, right? So the gain of, that means this circuit can be written if I know how to calculate the gain of common emitter amplifier using BJT. So looking at the same gain, I can write the gain of this circuit. Okay. Now let us try to short this resistor RS by using a bypass capacitor. Okay, let us say this one C2 shorts this resistance RS. Okay, so for high frequency AC signal, to improve the gain I need to short this resistance, so I connect this bypass capacitor. Okay. So now with this bypass capacitor the AC small signal gain can be calculated. Okay. So the AC small signal gain will be similar to this, but we will not have RS this time because RS is shorted by this C2. Okay. So the total gain is now equal to only this much. So this and this both are same. Okay. Okay. Now let us talk about this slide. This would be my last slide for the day. Okay. In the diode connected MOSFET, we said that the impedance looking into the drain. So this is 1 by GM1 parallel to R01. Okay. So to justify this, one can again draw the small signal circuit. Okay. So draw the small signal model circuit of this connection. Okay. So we draw the small signal model of an NMOS, GMV1 R01, source gate drain, and short gate and drain. Right. That is, gate is shorted to the drain via this, right? Now for this circuit I can find out the impedance looking into the drain side. Okay. So this is equivalent to saying you have connected a Vx, I mean this Vx by Ix. So this ratio will give me the impedance looking into the drain. Okay. So looking into the drain, that is this Rx. So this Rx is impedance looking into the drain, which will be given by the ratio of Vx and Ix. Okay. So for finding out this ratio, I can write this relation, that is this Ix. Okay. So the current Ix, which is coming here also, so this current Ix is equal to this current plus current through this. Okay. So current through this is GM1 V1, and since this potential, this node is at Vx potential, so this is also at Vx potential. Okay. So that means current through this would be Vx by Ro1. Okay. So I can write Ix is equal to GMV1 plus Vx by Ro1. Okay. Now from this Vx by Ix could be found. Okay. So simply I take Vx common, so Vx by Ix would be equal to 1 by Gm plus 1 by Ro1. Right, from here Vx by Ix is 1 by Gm plus 1 by Ro1, or this entire term, so this is equivalent to 1 by Gm1 parallel to Ro1. Okay. So that is, this impedance looking to the drain is equal to 1 by Gm1 parallel to Ro1, right, so which we had assumed. Similarly, one can find out the impedance Ry looking into the drain of PMOS, okay, by again drawing the small signal circuit and then writing the equation for this current Iy. Okay. Gate and drain are shorted. I mean, this small signal circuit and this both are same, right? No difference. So one can write Iy. So Iy would be equal to this current Gm2V1 plus current through Ro2. Okay. So this node is also at Vy potential. So Ro2 would be Vy by Ro2. Okay. So the total current Iy is given by this Gm2 V1 or Vy, because V1 is equal to Vy here, Gm2 Vy plus Vy by Ro2. Okay. Or Vy by Iy, which is also equal to the impedance looking into this port, drain. So this is equal to this much, 1 by Gm2 parallel to Ro2. Okay. So I'll stop here and we'll carry on from here itself in the next lecture.